For today's lesson, we're doing a quick comparison of ionic and molecular substances. Ionic substances are those that are formed from ionic bonds, while molecular substances are those that are formed by covalent bonds. Just a reminder, ionic substances are formed from ions, which we know are charged particles, but for molecular substances, because they are formed by covalent bonds, which include the sharing of electrons, there were no charges produced in those compounds. So the properties of ionic and molecular compounds will be due to the presence of these charges or the lack of charges in the compound. And the first property is the melting or boiling point. Ionic compounds have high melting and boiling points. Opposite charges are attracted to each other, and these electrostatic forces of attraction which are formed are very, very strong. So if we wanted to convert an ionic solid to a liquid or to a gas, a lot of energy would be needed to overcome these forces of attraction. And since a lot of energy would be needed, ionic compounds would therefore have a high melting point and would also have high boiling points. And because they have high melting and boiling points, they tend to exist as a solid at room temperature. Molecular compounds, on the other hand, have low melting and boiling points, and this is because they don't have any charges. Unlike the ionic compound, which has ions that are attracted to each other and they are held closer together, covalent compounds don't have any charges and they only have some weak attractive forces between the molecules. Because the attraction between molecules will be weak, remember there are no charges there, so they only have these weak attraction between the molecules, then only a small amount of energy will be required to break those forces of attraction. And since only a small amount of energy would be required, then molecular compounds have low melting and boiling points. Also, because there are weak forces of attraction between the molecules, molecular compounds exist as liquids or as gases at room temperature. In order for electricity to be conducted, there must be free, mobile, charged particles, meaning that we must have some charges to move around. And that's what electricity is, the movement of a charge. So ionic compounds can conduct electricity only when they are molten or dissolved, because in both of those cases, the ions would be free to move around. And we define ions as charged particles, so of course, if the ions are free to move around, they are able to carry a charge. Electricity would be able to flow. When ionic compounds are solid, however, we have to think back now to the states of matter. Solid particles, they're closely packed, they only have a small amount of energy and they vibrate in a fixed position. So we know that solid particles don't move from place to place. So ionic compounds, when they are solid, they do have the charges, but because the charges aren't free to move around, then the solid particles can't conduct electricity. Molecular compounds, again, these are formed when atoms share electrons, so no charges develop. And because molecular compounds have no charges, then they don't conduct electricity in any state. They don't have any charged particles to carry the electricity along. The final property of ionic and molecular compounds that we need to compare would be their solubilities. But before I can tell you about the solubilities, I need to tell you a little bit about water. So the water molecule, as we know, has the formula H2O, which means it has 2 hydrogen atoms and 1 oxygen. We should also remember this term from trends in the periodic table, electronegativity, which means the ability of an atom to pull electrons towards itself. Oxygen is more electronegative than hydrogen, so that means oxygen can pull electrons more than hydrogen can. Now I want you to picture tug-of-war. If you have 2 persons pulling on a rope and one person is stronger than the other, then the stronger person would be able to pull the rope more towards themselves. That's essentially what happens when oxygen and hydrogen are sharing electrons. Within each bond, we would have 2 electrons that should be shared between hydrogen and oxygen, but because oxygen is more electronegative, it can pull the electrons closer towards itself. So the electrons basically sitting close to oxygen. And since electrons are negative and they're hanging out near oxygen, oxygen picking up this negative behavior, oxygen develops what we call a slightly negative charge. And because hydrogen is essentially losing these electrons, I mean it's not lost completely, they're still sharing, but they're sharing it unequally. The hydrogen now lost that negativity, so the hydrogen atoms become slightly positive. Any compound, any molecule that have both a slight positive and a slight negative charge in that molecule, we call it a polar molecule. So all of that was just to show you that within a water molecule, we can have some slight charges. How does this affect solubility? In order for a substance to be dissolved, it must be able to form an intimate interaction with the solvent. So sodium chloride, for example, an ionic compound which has positively charged sodium ions and negatively charged chloride ions, can be dissolved in water, because guess what? The water has some charges. The sodium chloride has ions which have some charges as well. So the water and the sodium chloride can be attracted to each other. And that applies to all ionic compounds. Ionic compounds have charges, water have charges, so the water can be attracted to these ionic compounds. And after this interaction, once they're attracted, then and only then can water dissolve these substances. So we would then say that ionic compounds are soluble in water. Ionic compounds can be dissolved in water. Now for the molecular compounds. Remember, they are formed when atoms share electrons, so they don't have any charges. And since they don't have any charges, then the water won't be attracted to them. And since there is no attraction, there won't be any interaction. So molecular compounds are insoluble in water. While those explanations would cover almost all molecular compounds, we do have to highlight two substances that would not fit that mold, sort of our exception, and it would fall under our subtopic, which would be called allotropes. And allotropes are defined as different forms of the same element. The allotropes that we have to be familiar with are diamond and graphite. Now, both diamond and graphite are made up of carbon atoms, and these atoms are linked by covalent bonds. But how they're linked differs. So I'm going to draw for you the structure of diamond and the structure of graphite, which you should be able to reproduce. In diamond, we have each carbon atom being linked to 4 other carbon atoms. But what we also notice about diamond is that we have some hexagonal rings. Hexagon, hex, 6. So these rings would have 6 carbons. So if you want to draw a diagram to represent the structure of carbon, we can start off like this. Central carbon, which has 4 other carbons bonded to it, and 4 because carbon can form 4 bonds. But because they'll form hexagonal rings, we can just complete this portion to show how the ring is going to be formed. If you feel like it, you can just continue. But the key thing is that we must show at least one of the carbon which has 4 other carbons bonded to it. So we have 1, 2, 3, 4 other bonds, and then we just complete one ring. Show them that they have some hexagonal rings as well. For graphite, and this is where the difference comes in. Yes, carbon can form 4 bonds, but in graphite they're only forming 3, and they're also forming hexagonal rings. So we'd start with a ring and we'll just add to it. So we'll have 6 carbons linked together to form a ring. Once we have 2 rings joined together, then it would be essentially showing that the carbons in graphite are linked to 1, 2, 3 other carbons. These are 3-dimensional structures, so we could continue adding carbons to this indefinitely, but for our demonstration we simply need to show how they are linked together. So once we're showing that, we don't have to make our diagram too big. Alright, the second difference between diamond and graphite is that graphite actually exists in layers. And between these layers, we have some weak forces of attraction. To represent that, we use a broken line, because we know we use a dash to show a bond, but it's not really a bond, it's just a weak attraction that link the layers together, sort of holding it in place, but because the weak is not really holding it firmly in place. So these would be the structures that represent diamond and graphite. We'll have to talk about the differences. Now in diamond, we had each carbon linked to 4 others, which means all of the 4 valence electrons on carbon have been used up. But for graphite, we would see that each carbon is linked to 3 others. That 4th electron is going to become delocalized, meaning it's going to break free from the carbon. It doesn't belong to any one carbon anymore. And those delocalized electrons are free to move around the entire structure. Because of these now free electrons moving around, remember we need charged particles for electricity to flow. Right, so graphite, since it has these free electrons moving around, graphite can conduct electricity. Diamond cannot. And of course it can't because it doesn't have any free electrons. Right, one other difference. With carbon, we have each carbon being bonded to 4 others, and this continues indefinitely. And because we have this extensive network of carbon atoms linked together, then diamond is very, very strong. It's a very hard substance. It's actually the hardest substance. So they tend to use diamonds like in drill bits because it's that tough. It can break through almost any other substance. Right, so little fun fact, only diamonds can cut diamonds. That's how hard it is. Graphite, however, has these layers. So it's not this extensive network, but we'll have these layers that are held together by weak forces of attraction. Graphite is actually very brittle. So diamond is hard, but graphite is brittle because of these weak attractive forces. Graphite is actually used as your pencil point. So always hear the incorrect term that a pencil point is lead. No, pencil point is not made from lead, it's actually made from graphite. And as you write, those weak forces of attraction are broken and pieces of graphite will be left on your paper. And that's how your pencil works, just graphite. And we'll have these weak forces, so as you roll the pencil across, then you're breaking off little pieces of graphite. Graphite can also be used as a lubricant. So if you have a key that's getting stuck in a lock, you can always rub a pencil on that, break off some pieces of graphite, and as you try to put that key back into the lock, the graphite should be slipping across each other. Again, weak forces of attraction. As you rub it, it's going to slide. So it should allow the key to just slip into the lock. Alright, so that's our comparison of ionic and molecular substances with a little peep at allotropes of carbon, diamond, and graphite.